Now we can put this triple integral to rest. As we saw in the last couple of problems, what we wanted to do was compute this integral in Cartesian coordinates, and very difficult, very unfortunate integral. And we saw that the integral in cylindrical coordinates was a little on the difficult side. Easy to set up, but did not provide integrals that could be done in a reasonable amount of time. So what we did is we determined the spherical coordinate equivalent, and we came up with two integrals. And what we found is with both of these integrals, a reasonable integration process was available to us. So in order to compute this integral, remember we have to find a and we have to find b and add them. And so these integrals work out very simply. A is quite easy. Notice that all of these limits are constants, so we can separate out all of the integrals. So we have our d theta integral, we have our d phi integral, and our d rho integral. Of course, this integral is the easy one. That's just pi over 2. And of course, for here, we're going to need to use the power reducing identity. So we'll use 1 minus cosine 2 theta divided by 2, which we have here. And then, of course, this one is just add 1 divided by the new power. How easy, right? We have this right here. So now what we can do, when we substitute the 4 here, we just get 4 to the 4th over 4. That's just 4 cubed. So we go ahead and extract that. And then, of course, the pi over 2 times the 1/2 gives us pi over 4. Now here, of course, this is a fairly simple integral. We'll just get phi here. And of course here, we need a 1/2 from the chain rule, but the antiderivative of cosine is the positive sign, so we're just going to get a negative 1/2 sine 2 phi right here. So very simple integrals. And then, of course, the evaluation will be easy. Notice at the lower limit of 0, both of these terms are 0, so we only have to worry about the pi over 6. And of course, the 4 cubed over 4 is just 16, so we have a 16 pi. And then, of course, when we evaluate, we get pi over 6. And of course, 2 times pi over 6 is pi over 3, and sine of pi over 3 is root 3 over 2. And now it doesn't really make sense to try to push these together because you've got a pi here and a root 3 here. So what I did is I just multiplied this out. So we get a 16 pi, which is 4 times 4 pi squared, right here, pi times pi, divided by 2 times 3, which is 6. And then, of course, we get the 4 times 4 pi divided by 4. We've got the 2 2's here, which give us 4, times root 3 with a negative sign. Now what we can see, the way I've written it, the 2 divides into the 4. That gives us an 8 pi squared over 3, which we have here. And then, of course, these two 4's divide out, and we're left with a negative 4 pi root 3. So what we're seeing is this particular integral was very straightforward. Now let's look at b. Same thing, not as easy. The idea here is that we can separate out the d theta integral, but notice here our upper limit depends on phi, so we have to do these in the correct order. So now when we look at this, we've got our sine squared, and of course here we have our rho cubed. So that's just going to be rho to the 4th divided by 4. So when we evaluate, we get 1/4, and we just get the upper limit, 2 cosine phi raised to the 4th power, the lower limit just giving us 0. So again, another simplification there. Now, just for observation here, 2 cosine phi raised to the 4th power will just be 16 over sine to the 4th, because cosecant is just 1 over sine, so that reduces to what I've written here. We'll use that in the next step. Now what we need to do is notice that when we multiply all of this out, notice here we've got a 4, a 1/4 right here, and we've got the pi over 2 from this integral, and then of course we're going to factor the 16. And now when we compare these two, we have a sine squared over a sine to the 4th. That leaves 1 over sine squared, which is just cosecant squared. So that's the only difficulty of this integral, and it's not difficult at all. It's just a lot of busy work. Now what we see is that we have an 8 here, a pi, and a 16. That reduces to 2 pi, and this is a simple antiderivative. The antiderivative of cosecant squared is just the negative cotangent. Now again, very simple. We know cotangent at pi over 2 is 0, factor the negative, and then of course cotangent at pi over 6 is just root 3. So now we have negative 2 pi times negative root 3, which is 2 root 3. And of course, if you have trouble with the cotangent, just think tangent and take the reciprocal. Now, when we add the two, notice we still get the 8 pi squared over 3. And of course, when we add the 2 root 3, oh, and of course, sorry, I left out my pi here. Tragic. Let me write that in. So this is just 2 pi root 3. Yeah, this pi I need. So now when we add this term to this term, we end up with the negative 2 pi root 3. So that's the only difficulty of adding the two terms. So now what we see is that the original integral, as unfortunate as it was, is actually 8 pi squared divided by 3 minus 2 pi root 3. So I will say this again. The additional work that we needed to figure out the spherical coordinate representation was well worth it because the integrals were simple. Of course, it takes time to work through the triple integral because there's a lot of activity going on, but the execution was straightforward, so it was well worth the effort. And we are done.